All right, good morning. I'm Grant Merriman. I'm with Andon Specialties, and I'll be moderating this session. I wanted to introduce you to Stephane Millet. He's an application engineer at Sofraser, and he has educated in France with a master's in industrial engineering. He also has spent some time at UMBC in Maryland studying mechanical engineering. He started as an application engineer for Sofraser within the Elemental Enterprises Incorporated in 2024, and now he works as an application engineer at Sofraser's headquarters in France. Some of his hobbies include photography, music, traveling. He's been to Alaska, Yellowstone, the East Coast, and he loves basketball as well as baseball. And today is going to be talking about temperature-compensated viscosity and correlation and how this is a key to process monitoring.
Thank you, Grant, for the introduction. So today I'm going to talk about a major industrial challenge for viscosity measurement and how this innovative solution combining two well-known methods, TCV, temperature compensated viscosity, and correlation, can help and benefit your processes. So one of the challenges, how can we get reliable and useful measurements even when we have fluctuating process conditions? I'll share an industrial case, a customer in the body care industry. Then I'll explain the different steps of this method, the solution. And finally, I'll be talking about the results and the performances of this solution we have provided. I'll start with an important definition. What is viscosity? Viscosity, I think most of you know this definition. So viscosity is a physical property. It describes the ability of a product to flow under stress. Viscosity is a key parameter for many processes. It allows you to perform real-time process adjustments, avoiding product losses and drift or viscosity overshoots. It also allows you to continuously monitor viscosity to control and predict the final product's quality. However, in-process viscosity measurements in the industry is facing two challenges. The first one being the effect of temperature on the measurements, and most processes have their temperature change fluctuate, whereas the lab measurements are made under a reference temperature. And we know that the temperature changes a fluid's structural properties and thus changing the product viscosity. So the second challenges for the industrial viscosity measurements, in-process viscosity measurements, is that a majority of processes handle non-Newtonian fluids, and non-Newtonian fluids viscosity are changing depending on the shear rate. Depending on the velocity of a product, of how fast the product is pumped through the pipe, or for example, how it is agitated, how it's been stirred in a tank. And we have the major difference is that laboratory conditions, shear rate conditions, is that they are made under a constant shear rate, whereas in-process shear rate is usually unknown and varying. So we have different measurement conditions. We will then have different values, viscosity values. So to summarize the challenge, we have the industry that is used to labs sampling and doing lab measurements. And so the viscosity measurement is made at a reference temperature, a constant temperature, and under a laboratory rate, which is constant and usually known. On the other hand, we have the inline viscosity measurements that is providing continuous viscosity measurements at process temperature, and which is varying, which is changing as the process. And we also have this measurement that is made at process rate, and we don't exactly know this shear rate because it is a combination of the flow speed, the geometry, the pipeline, how it's been installed, how the installation is. So it is really hard to directly compare laboratory viscosity measurements to inline viscosity measurements. And this presentation is about explaining the solution we have provided by talking about this business case, this customer case in the body care industry. I'll start with an explanation on the MIVI sensor. In the 70s, Fraser patented the first viscometer using the vibrational technology at resonance frequency. Fraser has now more than 50 years of experience in viscosity, in viscometry. We have more than 40,000 users, viscometer users worldwide. We are present around globally. I'm going to talk about the working principle of the sensor. It is a vibrational type technology. On the right side of the drawing, we have the driving side. There is a coil where there is an alternative current that is going through this coil. This is creating an oscillating magnetic field. In front of this coil is a magnet. So the magnet is moving back and forth and creating the motion of the vibrating rod. To the left of this magnet, there is a second magnet, which is also moving back and forth. And the other coil is detecting the change in magnetic field, the change in this magnetic field, and then the coil is getting an induced current that's been created by the combination of a magnetic field and the coil. So we are able to precisely detect the motion of the magnet, and thus this motion is correlated to a viscosity. So a change in viscosity will result in a change in the motions and the vibrations amplitude. So we have on the top left side, we have a simulation. So we can see the vibration. The maximum of amplitude of the vibration is 0.2 millimeter. So this simulation has been amplified by 100 to be able to actually see the motion. We can not actually see it vibrate, we can feel it with our fingers. On the bottom left, we have a picture of the sensor that has been installed, the MIVI sensor. We can see the long rod it is the vibrating rod, the needle, and the smaller rod is a thermal well with a PT100 temperature probe. So we are able to get fast response for viscosity and for temperature as well. This sensor is not influenced by external vibration. It is also a clean-in-place technology because as it vibrates, anything that is close, that is on the rod is getting clean or getting away from the rod. It is a maintenance-free. There is no moving part. And we have had customers that have this sensor installed for more than 30 years, and they have had no issues with it. So now I'm going to talk about the industrial case, the customer who installed and used the solution we've provided for TCV and correlation. The sensor, the MIVI sensor, can be installed on a tank, that's location A, or on a recirculation loop, location B1, or on a main line. For this specific case, the customer installed the MIVI sensor on the recirculation loop, location B1. We can see it on the picture on the right. So the MIVI viscometer is measuring inline viscosity measurements with varying temperature, process temperatures, and at a shear rate, at a process shear rate that's unknown, and at under process conditions. And on the other hand, the customer is used to doing lab viscosity measurement, and he's using a lab viscometer. So we will compare. The goal is to compare inline viscosity measurements to the lab viscosity measurements with the solution, with the different step of the solution I will talk about. So once we have the two equipments, we are able to record. This is an example of data recording for a single batch measurement. We have a first phase on this graph. We have a phase of preparation, product preparation steps, where the product is changing, and it is following its expected evolution. So we can see the first phase, and then we have the final phase, more where the customer is used to do the sampling. We can see it on the graph. We have the viscosity, temperature measurements, and the sampling is also done at the exact same time. And we repeat the same steps for a larger number of batches to be able to build the TCV model and the correlation. So on the left, we can see the lab measurements made under lab conditions, which means at a reference temperature. Here on this graph, it is for this customer, it is 25 degrees C. It is also made under a constant shear rate in a lab condition. To the right, we can see the process, the inline measurements, which are made at different temperatures. We can see that the viscosities are different, also depending on the temperature. So one important thing is that since the lines are crossing, there is no obvious, no direct correlation that's possible due to the difference in conditions, measurement conditions. Our solution consists in two steps. The first step being calculating a temperature compensated viscosity at a reference temperature. The same reference temperature than what's made in a lab environment. For instance, here it was 25 degrees C. To build this model, we need to have a reference product. We need to know the behavior of this product, how it reacts, we need to know its behavior as a function of temperature This model, there are two different models. We can use a table, or there is also a standard for petrol-based products, the ASTM D341, which is a standard that is in our electronics, but we can also, it can also be used for other products, not just petrol-based products. We've been providing this solution for other products and other industries, and from our experience, it works as well. It works too in other industries. The calculation, the TCV calculations needs 3 inputs: the viscosity measurements at process temperature, the actual process temperature, and the information on the reference temperature. So now that we have calculated the TCV at reference temperature, now I'm showing you the graph, the results of this transformation, this calculation, using the ASTM D341 standard. So on the right side, we've seen before are the process measurements, the viscosity measurements made under process conditions. And using this ASTM standard, the TCV calculation, we are able to provide a measurements made at the same reference temperature than what's been measured in a lab environment. So the goal, the idea is that this TCV calculation allows us to take into account, to have a viscosity measurement that's unaffected by process temperature variations, providing a viscosity measurement at a constant temperature, at a reference temperature. So once we have done this first step, this TCV calculation, we can now work on the correlation. The objective of the correlation is to take into account the different in shear rates, in shear rate conditions. So we can see on this graph, bottom right, we have the step, the TCV calculation, and then now we will work on the correlation, so comparing this TCV calculation at a reference temperature to the measurement made at a lab, in a lab, under lab conditions. Based on the lab and compensated viscosities, we've gotten the results, this correlation that we can see on the slide. Using a linear trend, we obtain a rather good correlation. The R square is equal to 0.9, which means there is low dispersion. And we use this model, this model with new batches, with new data sets, and we can see the results here on this graph. So we are here comparing lab measurements made under lab conditions to the correlated, using our solution, which is using the first step, TCV, and then correlation. And we can see that now we can directly compare inline measurements to the lab measurements. We have a relative deviation that is less than 5%. And this solution really provides fantastic results. So initially, the difference in the measurement conditions wouldn't allow us to compare the inline measurements to the lab measurements. And now, using this solution, we can directly compare the lab measurements to the inline measurements. This solution is already implemented. It can be used on the MIVI and 9710 processors with this Freezer product range. it is available on the market and helps companies monitor their process so that they can directly compare and use what they are doing in a lab and compare it to the inline measurements. This case was with a company in the body care industry, but we also we have widely supplied this solution in the oil and gas for tar products, for bitumen and asphalt, for high viscosity products, and we have also provided solution, for example, for glue manufacturing industries. This solution helps companies and industrial to reduce sampling time, to reduce cost, and also allows industrial to compare directly those measurements to the lab measurements. So, thank you for listening and for your attention.
All right, thank you, Stephane. We've got microphones in the aisles here, and if you've got a question, please step up and ask it for the group to hear.
What's your criteria for selecting the reference sample? And the second thing is, what's the maximum temperature of the process sample that your instrument can handle?
Can you please repeat the first part of the question?
First, how do you select the reference material to correlate you showed in the graph where you use the reference material that you use to correlate to the process. Now, how do you select that reference material as a function to do the temperature effect? Yeah.
I understand that you're asking about how do I select the reference temperature?
Yeah.
So the reference temperature in this case was the temperature that the customer is used to measuring the viscosity in a lab environment. So here it is 25 degrees C because the customer is measuring using the lab viscometer at 25 degrees C, and the process temperature are usually higher than what are the temperature in a lab environment.
It's the reference, one of the charts you showed where you had the reference, you characterize the temperature behavior for a reference material and then correlate it to the process. So is this a different material that you characterize it on? You had a curve in one of the slides, which is an orange line versus a black line.
I'm sorry, I have not really understood the question well.
That's okay, we can go this. What's the maximum temperature?
The temperature, the maximum process temperature is about 300 degrees C.
C?
Yeah.
Okay, thank you.
I think the question I had was maybe similar to yours. When you look at the modeling that you have in different applications, is that something that you guys have already collected data on and share, or is this something that customers have to develop on their own every time?
So this is what customer have to work. They have to gather information, gather measurements in order to build the models. But we also we have customer where we cannot really share those information because of confidentiality agreements.
So y'all don't have any pre-canned models?
We are using the ASTM 341 standard for petrol-based product. I mentioned in the presentation. This also can be used for other products and other industries. This is based on our experience in the industry.
Okay. Do we have any other questions? All right. Thank you, Stephane.
Thank you, Grant.
We appreciate it. All right. Dr. Pawel, there you are. Let me pull up your data here. All right. So next we have Dr. Pawel Kluczynski with AirOptic, and he is the CEO and president of the board. at the company. He has a master's degree in physics, which he attained in 1997. He also has a PhD, which he attained in 2020 in the field of laser spectroscopy. He started his research with tunable diode laser methods in 1997, developing algorithms for data processing, and is the author of more than 20 scientific papers and the inventor of 14 granted patents in the field of tunable diode lasers, tunable laser gas analyzers. And from 2001 to 2010, he's been working with tunable laser gas analyzers at Siemens, and he then co-founded AirOptic in 2010, where he has been the CEO since. Today he's going to talk about mid-infrared tunable laser analyzers for SRU applications. So, thank you, Doctor.
Thank you. Okay, good morning, everybody. So, thank you for the introduction, and first of all, I would like to thank the organizers for opportunity to present this work at this conference. I'm very happy to be here again. And so I will talk about our new applications that we have been working on since basically the last 3 years, namely for sulfur recovery unit applications, where we developed two types of analyzers for this process, one in situ and the other extractive. So, does it work? Okay, thank you. All right, so that's the outline of my talk. So first of all, I will talk about the sulfur recovery unit and just a brief introduction. Then I will talk about our multi-laser technique. So basically, also recap, I had a presentation last year about it for other applications. Then I will proceed with this SRU applications of our analyzers. So first is the in situ TDL air demand analyzer, and the second is extractive hot-wet system for SRU continuous emission monitoring application. And finally, I will conclude my talk. All right, so what is sulfur recovery unit? So sulfur recovery unit is designed to convert the H2S in the sour gas into elemental sulfur and water vapor. And we had a nice paper about it on Tuesday, so I will not go into much details. But this process is very critical, and you need to control the ratio between H2S and SO2. It has to be 2:1 in order to optimize, to maximize the reaction. And so majority of the H2S is removed via the Klaus process, so up to 99%. And the Klaus process consists of two parts. First part is the thermal reaction, and the second is the catalytic reaction. And so as you see from the equations, this ratio has to be maintained in order to keep this reaction maximized. And so in order to do that, you have to control the air going to the furnace, basically to have the right composition of the fuel and the air. And for this purpose, you need a good and reliable and fast analyzer for SO2 and H2S. So as it was also shown on Tuesday, typically for these applications, UV analyzers are used because they are continuous, they are fast, and also can measure H2S and SO2 reliably. So we thought, okay, we have our tunable laser technology, also with the multi-laser. And then, so we thought, okay, let's see if we can do it with the mid-infrared light and using the lasers. So that's what I will talk about on the next slides. Okay, so this one shows the schematics of how our analyzers work. So I showed it last year, so for other applications, but a brief summary. So this is a standard, say, tunable laser absorption analyzer. So you have a transmitter on one side of the process, and you have a receiver on the other side. And then you send a collimated laser light through the process, and based on the absorption signal, you are able to determine concentration of the gas. So traditional TDL normally uses only one laser, so you are able to measure one or two or sometimes three components. but that's about that. So we have developed this multi-laser technique when we can put up to 8 lasers into one device. So it's done via a multiplexing process. So both electrically and optically, we are able to multiplex those laser sources. And then you can do traditional wavelength modulation spectroscopy on that. Yeah, so you are still having a decent sensitivity. So absorption in relative numbers is 10 to the minus 6. So basically a theoretical limit. But you are able to measure more than one component because you can measure at least one component with one laser. And in addition, we have also done application with not only the traditional indium phosphide and gallium antimodide DFB lasers, or the traditional diode lasers in the telecom band, but we also are able to combine interband cascade lasers, so as shown on the graph, light brown color, we can cover up to 6 microns. And moreover, we can combine those lasers together. So in principle, we have a very broadband coverage from 700 nanometers up to 6 microns, 6,000 nanometers. So it enables us to measure, to combine components like, for example, oxygen with NO, and we can also measure SO2, and we can measure H2S. So this is exactly what you need for the air demand analyzer. And one important thing is also that in each and every device, we put a reference cell inside the receiver unit. The cell is permanently there, so this is actually a fixed solution. And we use a surrogate gas as a reference. So I will show a slide about it and how is the principle of operation, but this is a very important part of the analyzer, so you ensure that we have a line locking algorithm on, and then you can also use this signal for auto-validation. And, but apart from that, for the user, this is just a standard TDL analyzer with 2 flanges, yes. And you can also use the same technique for the extractive analyzer. And one important thing is, of course, that for the TDL, it's very important that the temperature of the laser is stabilized with the, say, accuracy and precision of 1 millikelvin, and you have to do it for all the lasers separately. So I didn't show it on this graph, but this is also part of the design, how to make this temperature stabilization correctly. Okay, so what about wavelength selection? So as I mentioned, we can use 2 lasers here, so we have quite a good degrees of freedom. And H2S, shown in red, has several bands that we can use. SO2, a little bit less, so we focus on the 4 micron band, because you can reach it with interband cascade laser. There is another band at 7 microns, but then you need to use a quantum cascade laser, which is a bit more complicated to use, although possible. And so you also have to think about other gases in the gas matrix. So especially for this process, you have to be careful about water vapor. So we choose our lines appropriately so you don't have a problem with interference of other gases, and typically water vapor in this case. And otherwise, the absorption is very strong. So because we are talking about 0 to 4 and 0 to 2% volume for SO2 and H2S, which means we have a lot of signal. So you need a very short path to do a very good job. So that's not a challenge with the low detection limits. And so having that chosen, we are able to provide the following outputs. So H2S 0 to 4%, SO2 0 to 2%. Then we have a separate air demand output, which is just a formula shown here, with the scaling factor, which can be also chosen. In our case, it was 3.5. And last but not least, you have optical transmission, so you can control, say, the clean, if there is a falling on the windows or if something has happened with the laser, so you control the transmissions through the process. In fact, we give you 2 transmissions because for one laser, one, and for the second, the other. And so this is all you need to really maintain this analyzer in the field. So what are advantages of this setup is, first of all, there is no sampling conditioning systems. Like for UV system, you need to knock down sulfur because of the problem with elemental sulfur interference. We don't have this problem in mid-infrared. Fast response time, yes, all TDLs below 1 second is not a problem. So we have, of course, in situ measurement. And Of course, you still have to be careful about the position of atomic sulfur, but I will mention in a moment how we do it. And we have this continuous validation thanks to built-in inline reference cell, as I mentioned, which is permanently in the receiver unit. And last but not least, the lasers do not require to be exchanged every year. The typical lifetime is between 5 and 20 years. Yes, as you all know, it's more than 10 years is a typical number. So that so if this everything is installed correctly, this analysis is basically very low maintenance. Okay, so more in detail how it looks like. So we have this in situ cross-stack configuration. So we have a receiver and transmitter mounted on opposite side of the process. And then, so as I mentioned, spectroscopy is very simple, but the mechanics is a bit tricky because, so first of all, you need to weld two flanges on opposite sides with some reinforcement. Alignment is not a problem because typically the duct sizes are less than 1 meter, so you don't have a problem with misalignment, if you do it correctly, of course. But then we have to be careful about the position of atomic sulfur because otherwise, if you have a fouling on the windows, then you will lose transmission. So in our case, we have developed this method to use the steam for purging of the windows, so keep the windows clean. And the second function of the steam is to keep everything warm, so above 140 degrees C, so we don't have a deposition of the sulfur. So basically, this is more like a mechanical mechanical problem than the spectroscopical problem. But we learned that when you have this heat tracing and you have a proper insulation, then everything works correctly. We also control the temperature of the wetted parts, so we can also control the flow of the steam for the steam tracing. So that's the only trick we had to develop. And from the safety point of view, so our alignment flange also contains a high pressure window, which is a sapphire glass. And we tested up above 100 bar G. Actually, last we did the test was 350 bar G, is more than you need. But just to ensure that this is you don't have any leakages of the toxic gas. And we also helium leak test each flange. Okay, so that's on this slide is, yeah, so we used a little bit more detail about this steam tracing. So we use at least 55 psi G of the steam, so to ensure you have a hot enough steam for tracing. Then we have these insertion tubes shown on the graph in red. So for this process, they are made in Hestalloy, in fact, but you can use stainless steel. And also all the wetted parts were made in Hestalloy. And in between, you have the separation valve. So if something happens to the window, then you can actually close the valve and being able to work on the analyzer when the process is running. But actually, we didn't have to use it until now, since last 3 years. So, but that's just in case, this is additional safety mechanism. Okay, so this is how it looks like in reality. So we installed it in one of the refineries in Sweden back in 2023. And basically in a cross-stack configuration. So you can see on those pictures that you have the steam tracing and also the insulation material. And in the middle picture, we have this, we see the steam supply. So we control separately steam to transmitter and separately to receiver. And as I mentioned, we measure on each side the temperature of the wetted parts. So we are always above 140 degrees C. So this is quite a good solution. I mean, this is only manual control of the steam, but it worked fine. So only in the beginning we have to set the right values at the refinery. And this is, of course, hazardous area. So we have a purge solution. So for United States, yeah, it's class 1 division 2, but for zone 2, and for ATEX and ICX, we can also go to zone 1 if needed. Okay, so this, as I mentioned, was installed back in 2023, and the end user, since we came with this disruptive analyzer, they wanted to test, because they wanted to test with something they know, and it was a UV analyzer. So the installation was done very close to the sampling point of the UV analyzer, basically less than 1 meter, so we could compare measurements of both UV and TDL. And the test was running the whole year from summer 2023 to summer 2024. And since summer 2024, the customer is now using only our analyzer in the feedback control of the air demand. So this is the data we got from the customer. So what you see is 8-hour log. So in the upper figure, we see the air demand output, and the red one is a UV analyzer, and the blue is a TDL. So you can see that the agreement is quite good. So we follow the trend. We have a slightly better or faster response time, then we see more nuances. So it's not the noise, it's actually, we see more transit data, because as I mentioned, the signal is so strong that you have a very little noise on the SO2 and H2S signal. So the raw spectra looks very nice. And the same on the lower panel, you see the H2S and SO2. Also, the UV analyzer, SO2 is red and the TDL blue, and H2S is green for TDL and brown for UV analyzer. So you see that also they go in the opposite direction, SO2, H2S, so it means that you're measuring correctly. And then they also follow very closely, so TDL follows very closely UV analyzer. And then, so this was ongoing for 1 year, and then actually our availability was 100%, so there was no maintenance needed. And also one small detail you see, and the UV analyzer is every couple of hours doing this auto-validation, and TDL is using this built-in reference cell for continuous validation. And as I mentioned, we do not require removal of the elemental sulfur. The UV analyzer uses the Mister probe to remove part of the sulfur because it goes to before it goes to the measurement cell. Okay, a few words about validation. So we have this inline reference cell, so it's a reference cuvette, which is mounted on the receiver side internally, and it's filled with the surrogate gas. So it's not the gas we measure, it's a gas which absorbs very closely in frequency to the process measured gas, but it does not interfere. So it's as shown on the figure, the blue one is the measurement gas, and the reference is red. So they are less than 30 gigahertz in optical frequency, so you can tune it easily with one laser. But they are not interfering, so you can actually use this for line locking purposes for one, and secondly, you can output the amplitude of the signal through either analog output or with a Modbus. So you can see that if this value is constant and equal to 1, the analyzer is measuring correctly. So, and the filter response function of the analyzer is exactly the same, because as I mentioned, less than 30 gigahertz compared to hundreds of terahertz of laser central frequency is a very small number. So all the electronics reacts exactly the same for reference and process gas. And in the figure below, you can see actually the real raw spectra of SO2, H2S, and the blue one is the surrogate gas absorption. And they are just shown upon each other because it's the way the analyzer displays the raw spectra, but of course they are in different frequencies, yes, not overlapping. So you can also see that the raw spectra quality is quite decent. Okay, so this was the information about our in situ analyzer. And now I would like to show also more data about our extractive analyzer that we developed for sulfur recovery unit stack continuous emission monitoring. And this was solely developed for the Middle East market, so we had the challenge to provide the ambient temperature for the analyzer of plus 60 degrees C. So, and this had to be done hot-wet because the sample had to be maintained hot. So in our case, the analyzer is just a small part, and the remaining parts of the solution is that we have this probe and the sampling conditioning system, and also with auto-validation scheme to do a daily check of zero and span. So this probe was actually not developed by us, but it was developed by MNC in North America solely for this process. And then so everything is kept hot at 190 degrees C. So we avoid all the cold spots because otherwise we would have a problem with sulfur. And so we had to be careful about how to provide a good sample, hot sample to the analyzer. And that is shown here. So the analyzer, in fact, measures NO, NO2, CO, SO2, and oxygen. We can also add CO2 if necessary. And this was a requirement for the SEM. And so, in fact, this one uses 2 cells and 4 lasers. So we had to use separate lasers for separate measurements. So there was 2 ICL devices and 2 traditional DFBs. And 2 different types of cells. So one was a Harriot cell with 7.6 meters, and the other was just a single pass because we had so much signal, then we don't need to have a multi-pass solution. And an electronic box was outside, and everything was heat traced inside to 90 degrees C, as I mentioned. We even had to put this heated adductor module to ensure that when we connect the heated line with the analyzer, there was no cold spot there. So this was also electrically traced. And so the whole enclosure was IP66, and as I mentioned, we were able to provide ambient temperature from -20 to +60 degrees C, which was +60 C was a requirement for the Middle East. And we deployed it 3 years ago in one of the refineries in the Middle East, and we passed all these validation tests, and so analyzer was working basically without any issues, even during the upset conditions. So when SO2 went up to 1%, 1 volume percent. Okay, so that was about the extractive system. So basically, to conclude my talk, so our technology has been proven for air demand applications, so far only for the air demand and SRU SEM. We are also looking at other measurement points for this process, and like for TGT, for example. So analyzer has a fast response time, as I mentioned, less than 1 second. For extractive, it's a little bit longer because you have to calculate also that it takes some time to fill the cell, but it's less than 20 seconds. So the advantages of in situ is that there's no fouling issues, no sampling conditioning required, which normally was clogging. And very important fact that there is no spectral interference with atomic sulfur. So even during the upset conditions, we are just measuring fine and no interference problems. Continuous validation thanks to built-in inline reference cell with surrogate gas. So in the end of the day, you have a low maintenance of the analyzer and low cost of ownership. And last but not least, the extractive analyzer hot-wet configuration has been successfully proven for SEM applications. If you want to see the analyzer, I have this similar analyzer. It's actually combustion CO02 analyzer, but it's exactly the same form factor as for air demand in our booth 503. So if we want to see it, just really welcome. And thank you very much for your attention.
All right. Do we have some questions for Dr. Kluczynski? All right, here we go.
Thank you for the presentation. I have a question about the reference cell. What's the life expectancy of the reference cell, and do we have to recalibrate it?
Yeah, so basically the reference cell, we calculated it's like 30 years lifetime, so it's a really good seal. And but of course, if it leaks, then you have an alarm, because then there's a mechanism that sees that if you lose this amplitude of the reference gas, then you have an error signal. So then you can exchange it actually in the field.
All right, thank you very much. If we don't have any other questions, excellent. Thank you, Dr. Kluczynski. Oh, before you go. All right, next up we're going to have Serge Bays. He is the managing director at LimeSoft Incorporated, and he is a seasoned entrepreneur and executive with over 16 years of experience building and scaling technology companies. As the founder of LimeSoft, he has grown a market-leading international business specializing in emissions monitoring, regulatory compliance, and process optimization software. Deployed in over 20 countries, LimeSoft solutions support more than 10 Fortune 500 companies across the energy, natural resources, critical minerals, cement, and waste-to-energy sectors. Outside of work, he likes to donate his time through advisory and mentorship in his board roles at the Tech Alliance Accelerator. And he also mentors MBA students at Ivy Business School. He enjoys reading, hiking, and participates in research on improving gut microbiome to create various, to treat various diseases such as C. difficile. He's going to have to help me on that one. Multiple sclerosis and advanced pancreatic cancer. And today he's going to talk about fence line and SIMS ethylene oxide monitoring for EPA compliance. Thanks, Serge.
Hi, everyone. Thank you for joining me on this session. Today, I'll be talking about the latest regs from EPA with regards to ethylene oxide detection and monitoring, and our software solution used to control a multiplexer and a gas analyzer to collect the data from various sources, as well as report it for regulatory compliance. Oh, okay. Thank you. That's okay. Right. So a brief overview of importance of ETO monitoring is what is ETO. Ethylene oxide, also known as ETO, it's a carcinogenic gas. It's widely used in medical sterilization as well as chemical manufacturing, and exposure to it can lead to various cancer risks, not just for facility workers and employees, but there's been detection of it and the effects of it traced to outside the facilities and the surrounding communities as well. So that's what's been driving the latest EPA regulations and implementation in order to control and reduce ETO and exposure to ETO. The current systems, they lack quick response time, so a lot of the ways it's done is the sample sent back to the lab, and by the time you receive the information about the ETO concentration, it's already been a few days or weeks. So having something that's more real time would be very important for this type of application. High resolution and high sensitivity, they're really bringing down the detection limits to like ppb levels, 10 ppb and below. And the regulatory compliance reporting as well. So in order to have the data, then you need to also properly manage it and report it. So EPA is mandating SEMS as well as fence line and workplace monitoring. So there's three main regulations that came out, and our expected deadline for compliance are sometime around 2026, depending on what the regulation is. Two of them are concerning medical sterilizers, requiring reduction of 80% of ETO, as well as requiring continuous emissions monitoring and workplace monitoring. So there's the three main systems that I'll be talking about today. One is SEMS, continuous emissions monitoring. That's typically monitoring the effluent that's coming out in the stack from various plants or facilities. Number two would be fence line monitoring. So that's monitoring the concentrations in ambient air around the perimeter of the facility. And number three is workplace monitoring, which is similar to fence line, but monitoring various rooms and indoor concentrations of air in the facility. And the other regulation relates to synthetic organic manufacturing plants, and that also mandates a 98% reduction in ETO, as well as implementation of SEMS and tracking the structure removal efficiency as well, which we'll talk about at a later slide. So what are the technology requirements? Well, as some of you know, the regulations and air monitoring regulations sometimes can be long and difficult to digest. So we went through it, and our understanding and our summary of the regulations would be adoption of fast real-time emission monitoring systems, as well as workplace and fence line monitoring systems, compliance with the Performance Specification 19, as well as Procedure 7. So Performance Specification 19 is similar to your standard US EPA Part 60 performance specifications that mandates the SEMs, detection limits, linearity checks, drift specification, and things of that nature, as well as there's the Procedure 7, which mandates now the ongoing quality assurance of the systems after they've been installed. Detection of low ETO concentration. So there's currently various gas analyzer vendors. They're present at this conference, and they're proposing different techniques of measuring low ETO. The two specific techniques that we've seen are the cavity ring down and FTIR. Continuous data logging. So of course, now you have to obtain the data from these gas analyzers and accurately store them, manage the data, ensure there's data redundancy, ensure there's no data loss, as well as generate alarms if the data is invalid or if certain ETO exceedance is reached, and then provide control charts, alarm windows, trends, and generate reports for all of that data. And part of it, of course, part of the Performance Specification 19 is also ensuring that daily quality checks, meeting the drift specification, and meeting high availability. Sometimes it's 90, sometimes it's 95%, depending on the facility. So let's get into the overview of the system architecture and the design of the data acquisition system. So at the very top, you see the gas analyzer. So typically, everything to do with the gas analyzer and the sample handling, that's outside of the scope of the software, but this is where our scope starts, is we obtain the data from the analyzer, typically over Modbus TCP IP, and then as you can see, there's additional sensors. If it's serial Modbus, we just use a simple converter. If it's analog and digital outputs, again, you have a converter to digital. And then for the outputs, we use the same converter, a PLC or just a simple I/O module that would send the data from the digital commands to digital outputs to energize various solenoid valves. And that's very important when it comes to controlling the multi-sampler that we're going to be talking about. Then the controller and the data logger typically sits on industrial touchscreen, but it can also be installed on various form factors, such as DIN rail or server, depending on the requirements of the facility and the space allocation. And it collects, it buffers all the data, it performs system control, as well as has a HMI type of touchscreen on it, and then it syncs all the data to the main server that would typically be located in the control room, but can also be located in the same place. And that server would then do all the advanced processing, such as averaging, data validation, availability calculations, control charts, and reporting. And then the data from that server can be sent to the plant DCS or historian for further historizing and anything related to the plant activities that they might want to see from their emissions monitoring system, as well as to various remote clients and engineering stations. So let's get into the sample sequence control configuration. So for this particular application, specifically for the workplace monitoring, a single gas analyzer was used with multiple samples, up to 25 samples in total. They can be enabled and disabled, as you can see in this window. Each green box represents a sampling point, and then the order of sampling can be rearranged to however you want to measure them. And also the various parameters such as measuring and pre-measured time. So for the multi-sampler, the way it was designed is you would have one sample being primed while the other one's being measured. And then you would purge, after doing the measurement, you'd purge that, and the priming of the next one starts, and the one that's been primed previously would start measuring. And then you could set the different alarms. So for this application, it was a simple high alarm and minimal flow alarm. So if the ETO concentration reaches a certain limit, you get an alarm. And if there's a flow drops below a certain limit, that would also be an alarm indicating that you need to investigate the system and service it. So then we get into the main screen for the workplace monitoring system. So after that's been configured, this would be the typical operator screen where you can see all the 25 sample points. So at the top left, you can see that currently the sample point 1, its name, its concentration, and the timestamp of when the measurement was last taken. You can see that that one's being primed, and another one's being currently measured. You can see that the green means the data quality is good, orange means that high alarm concentration is active, and red means that high alarm concentration is active. And currently at the bottom left, you can see that stream number 18 is being purged. You can acknowledge these alarms as required, and you can put the system into maintenance or run a calibration. You can also change between real-time measurement and 8-hour time-weighted average. So 8-hour time-weighted average is something that's required by EPA for these latest ETO regulations. And change between ppb and ppm, but usually it's ppb because parts per billion, because that's the low detection limits that are required for this application. If you're going into ppm, then something scary is really happening. Over here, we have the validation and calibration configuration. So sometimes these words are used interchangeably, and it can be a little confusing. But typically, when we refer to validation, it's like a daily drift check with a known gas concentration. So you put from the cylinder, you put the known gas concentration into the system, and you measure it with the analyzer, and then you compare the measured value to the expected value from the cylinder. In this case, we can see the system's running under normal operation. We have currently the sample purge valve is active, and it's purging one and it's priming location 8. And you can see the results of the last calibration. So the span drift failed, and the expected values are 0 for 0 and 5042 ppb for span, and the span failed with minus 41.58, which would suggest that perhaps the span gas ran out or was disconnected. And over here is where you can control the calibrations. You can change the offset and slope of the calibration, as well as schedule the automatic calibration for various time and days, set 0 adjustments and span adjustments, put the system in calibration and maintenance, and change the stability and the purge time. So the system automatically detects when the gas is stabilized at 0 at span points, and if it never stabilizes, that after a certain timeout, the system just times out and fails the validation. And the calibration happens should you fail any validations. Now the analyzer is out of control, the data is invalid, that's affecting your data availability. So then you would, based on the 0 and span factors, you would do an adjustment to the data to calibrate the analyzer and bring it in line with those values for the data to become valid again. And in the next screen, you can see that this is where the button for calibration has been started, and now the 0 gas is currently running gas, and it's calibrating the 0 point, and the system's also in maintenance. And once that finishes, then the system would be calibrated and brought back within the expected values again. Over here, we're just talking about briefly about the limits, the drift limits. So if the analyzer is within 0 and 2.5% drift between the expected and the actual value, or 10 parts per billion absolute value, then you get a warning, but the data is still valid. As soon as you go above plus or minus 5%, or then you automatically fail and the data becomes invalid. So you'd have to do a 7-day span, 0 and span drift check to certify the system, and then you have to do daily or every 3 days, depending on the type of application, to maintain the quality assurance of the system. The other thing that's required for these regulations is the above span check. So if at any point the ethylene oxide concentration exceeds 200% of span for 2 consecutive hours, 1-hour averages, the analyzer must perform a span check, and it must read within 20% of the certified reference gas for the span cylinder. And if it doesn't, again, it counts as a failed span check, and now the analyzer is out of control. So when the analyzer exceeds the allowable limit and goes out of control, you have to first flag the data as out of control. You have to generate an alarm, and it will start negatively affecting availability based on the data validation rules, and you would have to take a corrective action. So typically that would be calibrating the analyzer and servicing it to make sure you bring it within limits. There is also a diagnostic log window, which would contain all the diagnostics for the analyzer as well as for the controller. You would have pump flow rates, various concentrations, statuses, alarms, and as well it would have a log window which has a text form of in real time exactly what sequence we're running, what's currently happening with the analyzer and the multiplexer, and all of that, of course, text data can be exported for audits as well, and there's an electronic record of everything that happened with the entire system. And the last one here is the destruction move efficiency. So what is a DRE, destruction move efficiency? That's typically when you have abatement systems of ETO. So what we do is we measure the concentration of ETO before abatement and after, and you need to ensure up to 99.94% removal of ETO, and that's typically on a mass basis, so in pounds. So the way we calculate that is we calculate the mass rates in pounds per hour based on the concentration and the molecular weight of ETO and the flow rate of ETO. So we convert that to pounds per hour, and then we convert that to, or kilos per hour, depending on which jurisdiction the system's installed in. And then we calculate the total amount of mass of ETO before abatement and after, and that's a simple formula of mass in versus minus mass out divided by mass in times 100, and now calculates the destruction removal efficiency percentage that's required by EPA. So that concludes my presentation on ETO monitoring for the latest EPA regulations. We talked about 3 different systems, workplace monitoring, fence line, and SEMS, and the various requirements that are mandated by EPA, and how a software system that acts as a controller, data analytics, and reporting system can work with the ETO analyzers to meet those EPA requirements. Thank you very much.
All right, thank you, Serge. Do we have any questions or clarifications that we need from Serge while we've got him? All right, I've got a couple of announcements. One, make sure that you're keeping up with your scoring paper. We will be awarding, after our 2 afternoon presentations, Best Paper Awards. We also have a special award that we would like all of you to hang around for this afternoon during the awards. And it is time for lunch, so we'll see you after lunch.
I think I already got one of those from the previous. I'll have 2 now. Thank